to be about acids and bases. And this is case of A, case of B. These are usually called ionization constants. But if you will look up here, usually equilibrium is considered KEQKSP, and acids and bases are case of A, case of B. But see the K's? They're all equilibrium, and they all give you an idea. You put in reactants, how much product will you get? In the case of acids and bases, again, it's something coming apart. The acid comes apart and gives you hydrogen. The base comes apart and gives you hydroxyl. So the strength of an acid or a base is based on how much it comes apart. Here we have an acid, HCl, comes apart into one hydrogen and one chlorine. If we put products over the reactants, raise the power of the coefficient, we have H and Cl on the top and your acid on the bottom. This is a mass action expression. It's the top and the bottom. The more hydrogen you get, the stronger the acid.
Can I move here? I can't.
Thank you. This is a base, magnesium hydroxide. It comes apart into one magnesium and two hydroxides. The products go on the top, raised to the power of their coefficient, and the base itself goes on the bottom. The more hydroxide you get, the stronger the base. Water itself, HOH, comes apart into a hydrogen or hydroxyl. Not very much. But pure water does come apart to the extent that per liter of solution you get 0.000001 mole per liter of solution. That's 1/10,000,000th of a mole. If we say in a liter of pure water, we get 1/10,000,000th of a mole of hydrogen and 1/10,000,000th mole of hydroxide. That is 1 times 10 to the minus 7 of each. And the P of the H then, or the negative of the log to the base 10 is a 7. And the P of the OH also, because it comes apart 1 for 1, the negative of this log, this is the log, and the negative of it is 7. So the pH and the POH of neutral water is both 7. So let's see what this means in terms of pH and strength. If you have 1/10 of a mole of hydrogen ion, that's 1 times 10 to the minus 1. The log to the base 10 is this, right? Minus 1. But the negative of the log to the base 10 then is a 1. In 1923, Sven Florenson decided that he didn't want to write out this long scientific notation, and he didn't want to write this number. So not only did he decide to use just a logarithm, he used the negative of the log. In math, when we use the negative of the log to the base 10, it's symbolized by a small letter P. So the P of the H, the negative of the log to the base 10, the hydrogen ion is 1. Therefore, the P of the H is 1. Same thing. Now suppose we have 1/1000th of a mole. That's 1 times 10 to the minus 3. The log is a minus 3. The negative of the log is 3. So the P of the H is 3. As the arithmetic value goes up, the actual value goes down. Yes? Because you're moving further and further to the right of your decimal. Okay.